I want to talk about finding roots of complex numbers. When finding roots, every complex number has 2 square roots, 3 cube roots, 4 fourth roots, and so on. Finding some of the roots is very much like we did in algebra. When you're solving this equation, z squared equals 9, you're finding the 2 square roots of 9. And we can solve this one by just taking the square root of both sides, and we get z equals plus or minus 3. Now, if we represented those so they look like complex numbers, we know that 3 is really 3 plus 0i, and negative 3 is really negative 3 plus 0i. All right, we don't generally write them that way, but we know they can be represented that way. And on the complex plane, that means we're looking at this number right here on the real axis and this number right here also on the real axis, because both of the square roots are real, 3 and negative 3. Suppose we were wanting to find fourth roots, like the fourth root of 16. Well, there are 4 fourth roots of 16. Often when people learn to solve this one initially for the solve this equation for the fourth roots, they take the fourth root of both sides, and even often remember to put in that plus or minus. So they end up with this, z equals plus or minus 2. Now those are in fact 2 of the 4 fourth roots of 16, but they are only the real ones. So we can algebraically do this a little bit differently. If we solve z to the 4th equals 16 this way, we'll get all four solutions to this equation, which are the fourth roots of 16. Let's subtract 16 from both sides. And let's factor, because we have the difference of 2 squares. Now this one factors with respect to the reals. This one does not. So let's actually solve each of these by setting them equal to 0. Z to the 2nd plus 4 equals 0. And while we could have factored this one further with respect to the reals, let's solve it the same way. So we would have, oops, somehow I changed to x's. Let's go back to z's. We often use z when we're implying that we want all complex solutions and not just real ones. So we have z squared equals negative 4, and we have z squared equals positive 4. And when we take the square root of both sides here, we have z equals plus or minus the square root of negative 4. And here we have plus or minus the square root of 4. So now we have the solutions of plus or minus 2i and plus or minus 2. So 2 of them were real and 2 of the solutions were non-real. And so we didn't get these non-real ones over here. But these are the 4 fourth roots of 16. Now let me show you on the complex plane how they look. This is the real axis. This is the imaginary axis. So when we're looking at 2 and negative 2, 2 could be here and negative 2 here. And remember, 2i would be up here and negative 2i is down here. So notice they're equally distributed around this circle right here. This circle that is of a radius 2, all of the roots end up on that point evenly distributed around the circle. And by the way, the same thing was true up here. These 2 square roots were evenly distributed around that circle, this circle of radius 3. Now this is fine for these particular problems, but what if we want the roots of something like 32? In other words, how would we solve z to the 5th equals 32? Or how about cube roots of numbers that aren't real? How about solving z cubed equals 10i? How would you find the cube roots of 10i? And we're going to explore both of these problems. So let's do it. So we're going to solve z to the fifth equals 32. And in doing so, we will have all 5 fifth roots of 32. Now I want to do 2 things. One, I want to remind you about de Moivre's theorem, and I want to convert this to its trig form. Remember, de Moivre's theorem says that if we had a number in the form r cosine theta plus I sine theta raised to a power, in this case we're going to be talking about the 5th power, we know that that would equal r to the 5th times cosine 5 theta plus I sine 5 theta. Our de Moivre's theorem tells us that. Now in this particular problem, this is our z to the 5th. I want to convert 32 to its trig form. It's a real number. We know that its magnitude is 32. And if you were to graph it, we know 32 is just the number over here. Its angle would then be 0. This is the number 32. So I can write it as cosine 0 degrees plus I sine 0 degrees. And I'm just going to work in degrees in this problem. You could work in radians. So if we know that a complex number raised to the 5th power needs to equal this, de Moivre's theorem now applies, and we know that r to the 5th cosine 5 theta plus I sine 5 theta needs to equal 32 times the cosine of 0 degrees plus I sine 0 degrees. Well, we want these 2 things to be equal. So here's what we can do. We can set r to the 5th equal to 32. And if we take the 5th root of both sides, we'll have a value for r. We'll have the magnitude. So our r will be 2, because this will always be a real number. Similarly, I want 5 theta equal to 0 degrees. Or, 5 theta equals 0 degrees, or any angle coterminal with 0 degrees, which means I can add 360 k, where k is any number 0, 1, 2, 3, and so on. If I divide both sides by 5, I will get values of theta. 0 degrees divided by 5 is still 0 degrees. 360 degrees divided by 5 is 72 degrees. And remember, this is for any k value that is an integer. But specifically, I want thetas that are between 0 and 360 degrees. So I'm going to substitute in k equals 0, 1, 2, 3, and 4, and I will get 5 values for theta. So if you do that, we substitute in k equals 0, and we would get 0 for this, so we have 0 degrees. Substitute in 1, we would have 72 times 1, which is 72 degrees. Substitute in 2, and we would get 144 degrees. And keep going, and you'll get 216 degrees and 288 degrees. So our roots, or the solutions to this equation, can be represented this way. We also often use z sub 0 or z naught, saying we're substituting in that 0. So here is our first root. 2 times the cosine of 0 degrees, whoops, that's a 0, plus I sine 0 degrees. The second root is what we get when we substitute in k equals 1. That gave us our 72 degrees. Is 2 times the cosine of 72 degrees plus I sine 72 degrees. and continue. I'm substituting in 144 degrees. And 216 degrees. And 288 degrees. And those are the 5 solutions to this equation. Those are the 5 fifth roots of 32. Now you might not want them in trig form. Maybe you would want them in rectangular form or standard form for a complex number. So you could punch these in on your calculator. Well, no calculator needed here with cosine of 0 degrees and sine of 0 degrees. But you could use your calculator. And I've already done that calculation. So let me pop those values up for you. And here they are. I just used a calculator to find these values. So these are the 5 fifth roots of 32. I want to also show you this. Here's a picture of these numbers on the complex plane. Right? Here is the 2. Here is the number that had an argument of 72 degrees, then 144. Notice they are equally distributed around this circle with radius 2. And these are our complex numbers that are the fifth roots of 32. Now I want to summarize what we just did in a format that would allow you to perhaps do it a little more efficiently. For finding the nth roots of a complex number, we have our complex number in trig form. We could find the nth roots by taking the nth root of the magnitude. Remember, that's what we did over at the previous problem. We took the fifth root of 32. And then we needed to calculate the angles that we needed. And here's a formula that we can use to do that. So for the next example, let's do it in a little shorter fashion, just using this formula. You can always go back to doing the problem the way we did in the previous example. This just uses those ideas in a little more efficient way. So here we go. We're going to find the cube roots of 10i. That means we're really finding the solution to this, the solutions to this equation, z cubed equals 10i. What are the 3 solutions to this equation? So we need 10i written in trig form. 10i is up here, remember? So its argument would be 90 degrees or pi over 2, depending on whether you want to work in degrees or radians. So z cubed equals 10, because we still have that magnitude of 10, times cosine of 90 degrees plus I sine of 90 degrees. This is the equation that we're solving. Now, here's our formula. Again, you can use the process that we did before, which is really equivalent to what we're going to do right now. Here's what we're going to do. The roots are found by taking the cube root of 10 times the cosine of our angle theta, 90 degrees, plus 360 degrees times k, divided by 3, because we're finding 3 roots, plus I sine 90 degrees plus 360 degrees times k, divided by 3. And we're going to substitute in the values of k equals 0, 1, and 2. So we might as well do that arithmetic first. Then we'll write out the roots. So let's put in k equals 0, and let's just do it right here. So we have 90 degrees plus 360 degrees times 0 divided by 3. So that's really 90 degrees divided by 3, and we get 30 degrees. Then we substitute in k equals 1. And we have 90 degrees plus 360 degrees times 1 divided by 3. And if you do the arithmetic there, you'll see that you have 150 degrees. And finally, we substitute in k equals 2, and we have 90 degrees plus 360 degrees times 2 divided by 3, and we end up with 270 degrees. So now our roots can be written in trig form this way. They are the cube root of 10 times cosine of 30 degrees plus I sine 30 degrees. The second root is the cube root of 10 times the cosine of 150 degrees plus I sine 150 degrees. And the third root, which we'll call z sub 2, is the cube root of 10, right? All of them have the same magnitude, times the cosine of 270 degrees plus I sine 270 degrees. And we now have the 3 cube roots of 10i in polar form or trig form. If you use your calculator to find values, I've already done the calculations. Let me just tell you what they are. This first one, you will have 1.87 plus 1.08i. Our second one will be negative 1.87 plus 1.08i. And the third one, you could find is exactly equal to negative cube root of 3 times I. I'm just pointing that out. But as a decimal, it is negative 2.15i. And last, I want to show you on the complex plane where those roots are. So here are the 3 roots, right there. So let's just draw our circle in the complex plane. And the radius of this circle, oh, I missed center a little bit, but we'll just assume the origin is at the center. The radius is the cube root of 10. So our roots are evenly distributed around the circle, and they are at 30 degrees over here, 150 degrees here, and 270 degrees here. So these numbers are represented by these points in the complex plane. So this is 1.87 plus 1.08i. This is negative 1.87 plus 1.08i. And this point down here is about negative 2.15i. And again, those angles were 30 degrees, 150 degrees, and 270 degrees. So I hope you can go take some roots of complex numbers now.